Good morning. All right, let's keep going with simple harmonic motion. All right, so the other day we started talking about simple harmonic motion and how it was a type of periodic motion. So again, what sets simple harmonic motion apart from other types of periodic motion is that it vibrates about an equilibrium or resting position. All right, so we started to calculate things with simple harmonic motion the other day whenever we started calculating the period. But today we're going to talk about how to measure a couple more things. All right, so before we actually start calculating and measuring, you do need to know just basic vocabulary for some of these things. All right, so again, we're going to be looking at a mass on a spring system first and how these three things, amplitude, period, and frequency, look on a mass on a spring system. And then we're going to look at it on a simple pendulum in just a second. All right, but this is just basic vocab that will be for both of them. All right, so amplitude, we kind of already have seen with our last set of notes and with our lab that we did the other day. All right, so your amplitude is your maximum displacement away from that equilibrium or resting position. All right, so the first thing that I want you to see is that it is a displacement. So our unit for amplitude is going to be meters. All right, so it's a measurement of length, a measurement of distance, okay? So what we have to really look at with amplitude is we have to remember that it's the maximum displacement away from the equilibrium position or that resting position. So here on this mass on a spring system, all right, that equilibrium is right there. So if I were to ask you to measure or show me the amplitude, you would either measure from this point to that equilibrium position or this point to that equilibrium position. All right, so either one of those are going to be the amplitude. But one of the things that a lot of people miss on this, whenever I get you to either measure amplitude or show me amplitude, like label amplitude, is that a lot of people try to give me from the highest point to the lowest point. All right, so a lot of people try to give me that whole thing, and that is not the amplitude. It's the maximum displacement away from that equilibrium. All right, so we're either looking at this as the amplitude or this. It's not from max displacement to max displacement. All right, now the next thing we have already talked about, we've already seen, and that's going to be our period. So our period symbol is that capital T because we know it is the time it takes to complete one cycle. So all of our times are going to be measured in seconds. All right, so that's how long it would take this to go from this point all the way out and then come all the way back into that starting position. So that's going to be one cycle. Now, frequency, it shouldn't be super new. All right, we talked about it last year in chemistry. You talked about it in 8th grade. You've seen this before. All right, the symbol for frequency is that lowercase f. All right, so, and if you think about what frequency is, it's how many times. So if you frequent, say, Chick-fil-A, for example, all right, that means that you go there a lot. All right, so that's just the number of times that you go there, say, in a week. Or if you're me, you go there like 3-4 times every week. All right, so that's what frequency is. It's the number of cycles per unit of time, or number of waves per unit of time, or number of vibrations per unit of time, or number of oscillations per unit of time. All right, so that's just the number of cycles per unit of time, and our unit of time, remember, is a second. So our unit for frequency is something called a hertz. But whenever we're trying to interpret what's going on with these, the hertz does not really help us. So we like to think about it in that cycles per second or waves per second or vibrations per second or oscillations per second. All right, so that's where we can break a hertz down into 1/second. So that 1 represents cycles, waves, or vibrations. So how many cycles happen per second? How many waves happen per second? So on and so forth. Now, the cool thing about period and frequency is that they are inversely related. So we know that if they are inversely related, that means as one goes up, the other one goes down and vice versa. So not only do we have our original 2 equations for period, all right, so we have the first one is the period of a simple pendulum. So it's 2 pi times the square root of length over acceleration due to gravity. And then we have the period of a mass on a spring system, which is 2 pi times the square root of mass over spring constant. We now have another equation for period, and that's the inverse of the frequency. And we know that frequency is the inverse of the period. All right, so we now have 3 different equations to solve for period. So you have to know, you have to be able to distinguish which one you have to use for whatever problem you're looking at. All right, so we looked at what an amplitude looked like, period, and frequency looked like for this mass on a spring system right here. This is just what it looks like for a simple pendulum. All right, so your amplitude is just, again, the maximum displacement from your equilibrium. So if that straight down is our equilibrium position, it's going to be the degrees. We do not use radians, we use degrees away. All right, so meters is usually used for distance on a mass on a spring system. And then we use degrees for pendulums. All right, period, again, is just the time that it takes to go forward and then come right back. All right, so that's going to be measured in seconds. And then frequency, yet again, is hertz, which is also 1/seconds. And then you see this right here. That's just whenever something is in the denominator, you can put it to the negative first power, and that's the exact same thing. All right, so again, that's the number of cycles or vibrations per unit of time, and our unit of time is going to be seconds. Now, this is a really cool thing. This is what's going to lead us into the second part of this unit. All right, if we were to graph on a distance versus time graph, all right, if we were to graph the motion of either a pendulum or a mass on a spring system, you would see that it would create this shape. All right, so that's what this is. So we have the resting position of that mass on a spring system. We compress it, it goes up here, we let it go. It's going to go through that equilibrium position, stretch out. Through that equilibrium position, compress. Through that equilibrium position, stretch out. So on and so forth. All right, so whenever we connect these, they do create this wave. All right, this is something called a sine wave. All right, and sine waves, or just any type of waves, follow simple harmonic motion as well. That's what we're going to get to next week. All right, so on these waves, not only do you need to know how to calculate amplitude, period, and frequency on these mass on a spring systems and pendulums, you also need to know how to identify them and calculate them using these graphs that look like waves. All right, so on a wave, you have different parts. So you have these parts that are the highest points, those 3 pink dots. Those are all called your crests. All right, so the crest is the highest point on a wave. All right, you also have the lowest points on a wave. Those are called your troughs, okay? So here you have your resting position, which luckily for this problem is on our x-axis. So our resting or our equilibrium position is on our x-axis. So if I asked you to show me or to label what the amplitude was, it's either going to be from your resting position to your crest or your resting position to your trough. Remember, your amplitude is from your resting position to the maximum displacement, and that's what we see here. The next thing, so before we move on, I do want to make mention. All right, so most of the time, the resting position or the equilibrium position will be at that x-axis. All right, so say this was a +5 and then this was a -5. Your amplitude would just be 5 meters away from that resting position. But there are going to be some times that you will see that maybe your highest point is at that +4 and your lowest point, say, is at a -2. Well, that tells you right then and there that x-axis is not your equilibrium. All right, that's not your resting position. All right, so in order to figure out what your amplitude is and where your equilibrium position is, you would use this equation. It's just 1/2 of the highest point minus the lowest point. So if we use this equation or our numbers here, that's going to be 1/2 of a +4 minus a -2. So that means that we are subtracting a negative, which is like adding a positive. So that's 1/2 of 6, which means our amplitude would be 3 meters or 3 centimeters or 3 millimeters or something like that. All right, which means that our equilibrium position would have been at that 1. All right, so our equilibrium position would have been at like 1 centimeter because that means that 3 above and 3 below. Okay, so the last thing that I want to talk about how to look at and measure on here is something called a wavelength. All right, and if you think about what wavelength sounds like, that's the length of one wave or the length of one cycle or the length of one vibration. All right, so we could measure that either from crest to crest. That is one wavelength. Also, the symbol for wavelength, we did see this last year in chemistry. It looks like an upside down Y for lambda. All right, that is one wavelength. You could go from trough to trough. That is one wavelength. Or you could go from the beginning of this wave to the beginning of that wave. That is one wavelength as well. You could also just pick a random point on this wave and go to the same exact point on the very next wave. That is also a wavelength. All right, so you just have to pick one point and then go to the very next point on, or the very same point on the very next wave. All right, so that's what we see right here. All right, so on this graph, the first thing that I want you to do is make one cycle of the object's motion. All right, so if we start at the beginning, that's a crest, so we would go to the next crest. That is one cycle. All right, if we did troughs, we could go from the first trough to the very next trough. That's going to be one cycle. All right, if we did, say, the beginning of this wave to the very beginning of the next wave, that's going to be one cycle. All right, we could also say this random point, so this is like halfway between that crest and trough, we would have to go to the very same point on the very next wave. All right, so all of those are examples of one cycle. All right, now this one says, where does the first cycle end? All right, so our wave actually began as a crest. So where does that next crest happen? And that's at 2 seconds. All right, the next one asks, how many complete cycles do I have on this graph? All right, well, I have a crest to start off with. So that's, oh, I don't want it to do that. All right, so I follow that. That is one wave or one cycle. And then I have another wave or another cycle. All right, so I have 2 complete cycles happening here. All right, now the next thing I want to know is what is the amplitude of each vibration. So my highest point is a positive 100 and my lowest point is a negative 100. That's fantastic. That tells us that our equilibrium position is at 0. So the amplitude is going to be 100 centimeters. All right, and I got that centimeters from our unit on that y-axis. Now, the last 2, the period of each vibration. So that is how long it takes for one cycle to occur. All right, now we could use whatever points we chose. All right, so if we chose these points, all right, that's from crest to crest. So it ended at 2 seconds. All right, so that 2 seconds was how long it took to occur. Well, what if we started right here and went to this point? It's the same exact point on the very next wave. All right, so you would do 3 minus 1. 3 minus 1 is 2 seconds. All right, what if we chose the beginning of this point to the very same point on the next wave? So that would be 3.5 minus 1.5, which is 2 seconds. So it doesn't matter what points you choose as long as you're choosing the correct points, not only that, but then subtracting. So the period of each vibration is 2 seconds. Now, the very last thing that I have asked you to solve for is the frequency. All right, so we know that frequency is the inverse of the period. So we take 1 over our period, which was 2. If you leave this as a fraction, I will mark it as incorrect. I want you to divide them out. So this one's really easy. 1 divided by 2 does give us 0.5 hertz. So that means that half of a cycle occurs every single second. And even if we didn't have this equation, we could have looked at our graph. All right, we could have looked at our graph and seen that at 1 second, there was only half of a cycle. All right, so that's knowing how to do this on a graph. Let's look at some examples. So this first example, we have the reading on a metronome, which indicates the number of oscillations per minute, the number of vibrations per minute, or the number of cycles per minute. All right, I want to know what is the frequency and the period of the metronome whenever it is set at 180. All right, so that means that there are 180 cycles, 180 oscillations, 180 vibrations that are happening every 1 minute. All right, well, what I've given you right there is a frequency. All right, but our frequencies, our units of time are not minutes, they are seconds. All right, so we have to turn that into hertz, which is 1 over seconds. So all we would do would be divide that 180 cycles or oscillations or vibrations by 60 seconds. Whenever we divide 180 by 60, we do get 3 hertz as our frequency. That means that 3 cycles occur every single second, or 3 waves or 3 oscillations occur every single second. All right, so that's the frequency. I also asked you to solve for the period. We know that period is the inverse of the frequency, so we just take 1 divided by 3. Again, do not leave it as a fraction. If you leave it as a fraction, I will mark it as incorrect. All right, so we divide it out. 1 divided by 3 is 0.333333. So our period is 0.33 seconds. That means that one cycle occurs every 0.33 seconds. All right, this next example says a child swings on a playground swing that has a length of 2.5 meters long. All right, I want to know both the period and the frequency of the child's motion. All right, so the first thing that we need to realize is that the playground swing acts as a simple pendulum. So before we solve for frequency, we have to solve for the period of that simple pendulum. So we have to use our very first equation. So T is equal to 2 pi times the square root of the length over acceleration due to gravity. We do not have to rearrange this, so we can just plug in our numbers and go. So we have 2 pi times the square root of 2.5 divided by 9.81. That gives us a period of 3.17 seconds. That means that it takes 3.17 seconds for that child to swing forward and then come all the way back. All right, now I want to know what the frequency is. We know that frequency and period are inversely related, so we take the inverse of our period. So that's 1 divided by 3.17 seconds, which gives us a frequency of 0.315 hertz. So that means that 0.315 cycles happen every single second. And last but not least, we have a spring that has a spring constant of 30 newtons per meter. And we're attaching that same spring to 2 different masses and then setting it in motion. All right, I want to know what is the period and the frequency for both of the systems. All right, so we're going to put our 2.3 kilogram mass on this side. And then we're going to do the 15 kilogram mass on this side. All right, so this is a mass on a spring system. So you should know that we're going to have to find the period of a mass on a spring system first before we can find the frequency. And we're going to have to use our second equation. So period is equal to 2 pi times the square root of the mass divided by the spring constant. So we're going to use that same equation for both masses. All right, now for the smaller mass, 2.3, that's going to be 2 pi times the square root of 2.3 divided by 30. While the larger one will have 2 pi times the square root of 15 divided by 30. Again, we do not have to rearrange this. It's just a plug and chug problem. So for our smaller mass, that gives us a period of 1.74 seconds. That tells us that the smaller mass goes forward and back in 1.74 seconds. The larger mass, whenever we calculate it out, has a period of 4.44 seconds. All right, so that means that the larger mass has a longer period. So we see that direct relationship between mass and period here. All right, now I want to find the frequency for both of these. So I take the inverse of the period for both of those. All right, so on the first one, that is 1 divided by 1.74 seconds, which gives us a frequency of 0.57 hertz. That tells us that 0.57 cycles happen every single second. And then for our second mass, our larger mass, that's going to be 1 divided by 4.44 seconds, which gives us a frequency of 0.23 hertz. All right, so if we look at that, we see that the larger period, that 4.4 seconds that came from the larger mass, has a smaller frequency. And the smaller period, the shorter period, has a larger frequency. So we can see that inverse relationship happening here. All right, y'all know if you have any questions, you know where to find me. Have a good one.